discuss about the respiratory mechanics during controlled ventilation. First of all, I would like to make a very quick reminder about what is the basic functioning of breathing, which basically is a game of pressures. Here you have a very simple representation of what the respiratory system could be with the two components. The first is the lung with the airways here and the lung parenchyma embedded into the chest wall. And the key pressures are shown here. The first is the PAW, the airway pressure, or the pressure at the inlet of the respiratory system, if you will. And the goal here is to propagate the airflow from the atmosphere here down to the alveoli. And during this travel, the air has to overcome different forces to result in the inflation of the respiratory system by the tidal volume. The first is the resistive forces, in particular the airway resistance, and in particular the airway diameters. And the second is the elastic forces coming from both the lung and the chest wall. The second key pressure is the alveolar pressure. We can obtain from the airway pressure, and we'll come back on that very soon. And if you refer the alveolar pressure to the pleural pressure that surrounds the lung, you get the transpulmonary pressure. And this very simple representation can be also expressed in terms of this very simple equation, which is named the first equation of motion of the respiratory system, that tells us that at any time during the insufflation, the airway pressure is a sum of three pressures. The total PEEP, which is the alveolar pressure at the end of expiration, the starting point, if you will. Then a pressure that is a resistive pressure that incorporates the flow and the resistance of the system. And a third pressure, which is the elastic pressure that includes both the tidal volume and the elastance of the respiratory system. And you see that there is even a fourth pressure with a negative opposite sign, which is the Pmus, shown here, who is going to happen once spontaneous breathing is present. But since my talk is dedicated to the controlled mechanical ventilation, we are going to assume that Pmus equal to 0, and this equation simplifies as shown here. You have three pressures on the right-hand side, and even two pressures if you move the PEEPtot from the right to the left-hand side, and if you analyze the change in airway pressure over time above the starting point, I mean above the end expiratory alveolar pressure. And my talk also will be focused on the airway pressure and will not be dealing with the transpulmonary pressure. So I selected three targets to illustrate with the corresponding pressures: the deformation, and we are going to look at the elastic pressure; the resistance, and we are going to look at the resistive pressure; and the dynamic pulmonary hyperinflation, looking at the measurement of intrinsic PEEP or PEEPi. And I would like to conclude with an example of a combination of the three basic signals: the pressure, the flow, and the volume. So let's start with the elastic pressure, which is not totally logical because it is not the first pressure in terms of chronology, but for reason of simplicity, I started with the elastic pressure. Here you have a typical tracing of an ARDS patient received invasive mechanical ventilation under sedation and paralysis in volume control mode, constant flow inflation. You have the inspiration up here and the expiration down there, and you have here the airway pressure. So the goal here is to measure the elastic pressure. And to get it, you have to discard the resistive pressure. And to do that, the simple way is to make the flow equal to 0. And to make the flow equal to 0, you have to make an inspiratory pause, closing the airways at the end of inspiration. And we have performed here, we have interrupted the flow at this point, at the end of insufflation. We have 0 flow here, and you observe the change in airway pressure during this occlusion from the peak airway pressure to the plateau, which is obtained here after a certain amount of time at 16 centimeters of water. The first immediate pressure drop is the resistive pressure, and we are going to deal about it later on. And we know from the evidence-based medicine that this value should be maintained as much as possible below 28 to 30 centimeters of water. There is a second way to obtain the same elastic recall pressure, which is without any maneuver. You have just to accommodate the setting to obtain a very short period of 0 flow by manipulating the tidal volume, the respiratory rate, the flow, and the inspiratory time during the inspiration here. And you get here, breath by breath, a value which is more or less close to the elastic pressure obtained here, which is named the plateau pressure in the intensive care jargon, if you will. Many of you probably use pressure control ventilation in ARDS patients, and the question could be, should we measure or can we measure plateau pressure during pressure control ventilation in a mode in which we set the pressure? Not only we could, but also we must, and in a case like this, observe first the decelerating shape of the inspiratory flow in pressure control ventilation, but here, at the end of inspiration, the flow is not equal to 0, meaning that the pressure you have set here in pressure control is really not the elastic pressure. And indeed, you can perform an inspiratory occlusion, and you observe here a rapid immediate drop, which corresponds to the resistive pressure, and actually you obtain here the elastic pressure, which is far to be different from the pressure you set at the ventilator. So the driving pressure is a second elastic pressure. It's just the difference, or the trajectory, if you will, of two elastic pressures. The pressure at the end of insufflation, we have measured previously, and the starting point, the alveolar pressure at the end of expiration. The simple equation is shown here. And in a patient like this, we got almost 11 centimeters of water driving pressure. But I would like to draw your attention to the fact that in a case like this, the flow at the end of expiration is not equal to 0. It's still positive, indicating that the value you have here, which is a PEEP set at the ventilator, is lower than the real and expiratory alveolar pressure at 0 flow, and therefore the driving pressure here is overestimated. And driving pressure is very popular in the present time, in particular from this study by Marcello Amato, showing that there is a statistical relationship between the risk of death at the hospital discharge and the driving pressure, with a threshold in the vicinity of 15 centimeters of water. However, we have no enough level of evidence to recommend using this target in the routine practice of mechanical ventilation regarding the driving pressure. You can now measure really the intrinsic elastic characteristic of the respiratory system, the elastance, or which is the inverse of the compliance. From the same graph, I added a new value here, 6.6, which is the expiratory alveolar pressure obtained after having really occluded the airway at the end of expiration. And here we have made a measurement at 0 flow. And from this from these three numbers, we can compute the compliance as the ratio of tidal volume to the driving pressure. And we got a 36 ml per centimeter of water compliance for the total respiratory system. The normal value is 100 ml per centimeter of water. And why it is important to measure the compliance? It is because, as previously found by Luciano Gattinoni by using the CT scan, it is a reflection of the baby lung, of the normally aerated lung. And in a case like this, moving the compliance from 100 to almost 36 means that you have lost something like 60% of aerated lung. And if you get back to the formula of the compliance, the ratio of tidal volume to driving pressure, that means that the driving pressure is a ratio of tidal volume over compliance. That is a ratio of two volumes, the tidal volume here and the compliance there, which is a reflect of the baby lung, and therefore is a rough indirect reflect of the strain. Here you have a typical value in the normal situation of the elastance. Note the units are different, centimeters of water per liter. In a normal subject, you need 10 centimeters of water to inflate the total respiratory system by 1 liter. 5 are taken by the chest wall and 5 by the lung. And you have here the additional property of the elastance of each of the component of the respiratory system. In ARDS patients from pulmonary origin, with an impairment of the elastance, an increase in elastance, again, which reflects more a reduction in the aerated lung than an increase in the elastic property of the lung, For a normal chest wall, you get an increase in the respiratory system elastance. And if in the same case, for the similar impairment in the lung elastance, if you have an increase in the elastic property of the elastance of the chest wall, you have a much greater value of the total respiratory system elastance in this case as compared to this one. Another consideration regarding the elastic pressure is the stress index. In this case, you have the relationship between the airway pressure over time during insufflation, in particular during the constant part of the constant flow inflation during volume control. And the relationship of pressure over time in this case is the same as the relationship of pressure over volume, whose slope is the elastance. So here you have the elastance, and this author went a step further by fitting this simple equation to this data, and in particular introduce this exponent B, which is a stress index. It tells us how much the pressure is going to change in proportion to the change in time, meaning in terms of volume. In a case like this, with a B equal to 1, the elastance is constant. There is a proportional increase in pressure and volume. But on the right-hand side here, the stress index is greater than 1, meaning that you have a progressive increase in elastance, a decrease in compliance. In particular, at the end of insufflation, there is a more increase in pressure in proportion to the increase in volume, suggesting overdistension, and should the target of the stress index be 1, to move from here to there, you have to reduce either the tidal volume or the PEEP. And by contrast, on the left-hand side here, the stress index is lower than 1, meaning that you have a progressive decrease in elastance, an increase in compliance over the time of inflation, indicating some recruitment during the tidal breath, meaning that during the subsequent expiration you are going to de-recruit, and the subsequent inspiration to re-recruit, a pattern suggestive of atelic trauma. And to move from here to there, you will have to increase the PEEP, for instance. But again, we have no strong evidence in the literature suggesting first to use a stress index, and second, to target 1 as a value for the stress index. Now let's move on to the second pressure we have to measure, which is the resistive pressure. And again, to obtain the resistive pressure, we have to discard the elastic pressure. And to do that, again, we have to apply a very old respiratory physiology method, which is the elastic subtraction method. That is the reason why I started with the measurement of elastic pressure. From the peak airway pressure, you are going to subtract the elastic pressure. And the total pressure drop here is a resistive pressure across the whole respiratory system. And if you divide this pressure drop by the flow, you get the resistance of the whole system. So you have seen that we can easily measure the total elastance and the total resistance that apply across the respiratory system. And I would like just to draw your attention on the esophageal pressure signal in the middle, just to show you that there is no into the chest wall the equivalence of airway resistance, of resistive component, as compared to what happens in the airways, which makes sense. And you finally make a step further by partitioning the total pressure drop into 2 components based on the pressure at the first zero flow. You have here the immediate pressure drop to the peak, from the peak to this pressure at the first zero flow. That corresponds to the airways resistance. And the second additional slow decay down to the plateau corresponds to an additional resistance which is thought to reflect viscoelastic forces or lung inhomogeneity across the lung. We have been measuring the inspiratory resistance, but the resistance are also high during expiration and even higher during expiration than during inspiration. Here on this table, I showed you the resistance and the compliance in a normal subject. You remember the normal value of compliance is 100 ml per centimeter of water, 1.1 liter per centimeter of water. A typical Normal value of resistance is 5 centimeters of water per liter per second. If you multiply these two terms, you get a time, which is 0.5 seconds, which is named the time constant, which is the time required to deflate the lung from the volume at the end of inspiration by roughly 60%. And it is commonly assumed that we need 3 to 4 time constant to reach FRC. So in a normal subject, you will need 1.5 to 2 seconds to reach the FRC. But in a COPD patient or severe acute asthma patients, the resistance is very much higher. The compliance is higher due to emphysema, and therefore the first time constant is very much higher, 3 seconds, meaning that you need 9 or even 12 seconds for the FRC to return. And if you look at what happens for the respiratory rate for a 3-time constant value, you get a respiratory rate to 7 breaths per minute, which is difficult to sustain for the patient or even to set to the ventilator. And here it is just a graphical representation of what I was been telling you. Here you are at the end of insufflation, you have to deflate this amount of gas. Here you have the 1-time constant for a normal subject, and you see you have plenty of time to reach the FRC in this case. In a COPD patient, it's another story. Here you have the first time constant, and you see that it will be very, very difficult for a patient like this to reach the FRC in a reasonable amount of time. And the consequence of this is very important because it is the main mechanism by which there is a dynamic pulmonary hyperinflation. Just to draw your attention to the fact that dynamic doesn't refer to spontaneous breathing. We may have dynamic pulmonary hyperinflation in passively mechanically ventilated patients. It's just a discrepancy between the expiratory time and the expiratory time constant. And therefore, there is no enough time for the FRC to return. And you see that breath by breath, due to the excessively high expiratory time, the FRC is progressively increasing up to a plateau due to a new equilibrium. And you see that in the same time, there is an increase in the inspiratory lung volume, making it closer and closer to the total lung capacity. And the difference here between the volume at the end of expiration during the mechanical breath is higher than the expected FRC, and this volume is named dynamic pulmonary hyperinflation or trapped volume. It is a patient in our unit with acute severe asthma, invasively ventilated with in volume control mode, and he was receiving 0 centimeters of water external PEEP. And in these patients, at this time, we disconnected him from the ventilator, and we were continuing to measure the lung volume. And you see that the difference between the inexpiratory lung volume during the mechanical ventilation to the point of 0 flow, corresponding to the FRC, was 1 liter. This patient trapped 1 liter of gas. And at this point, we resumed the mechanical ventilation. And you see it took some breaths for the previous state to recover. And at the same time, observed that there is a progressive increase in the PEEP peak due to the fact that the intrinsic PEEP is going to happen. And indeed, the corresponding pressure of the dynamic pulmonary hyperinflation is named the intrinsic PEEP. And you were suspecting it by looking at the expiratory flow over time tracing, showing that at this point, you have still an expiratory positive flow. And you can confirm that the alveolar pressure is actually higher than the atmospheric pressure by performing an inexpiratory occlusion. And you got here an increase in pressure up to a plateau, which corresponds to the total PEEP, or the inexpiratory alveolar pressure. And you see that you have here the expiratory driving pressure from 18 to 0, which is the pressure gradient that explains the persistence of a positive flow at the end of expiration in this patient. You may obtain a dynamic intrinsic PEEP if you measure the pressure at the first 0 flow just after opening of the inspiratory valve. And many years ago, this ratio, dynamic over static PEEP-I, was taken as an indirect reflect of lung heterogeneity, but that was not really successful to use this ratio. And I would like to conclude with some data we obtained recently in ARDS patients and published in the Blue Journal, where we combine the pressure, flow, and volume signal. Here you have a patient ventilated at 5 centimeters of water of PEEP, in whom we we build the flow volume loop. The inspiration is here, then the patient is going to exhale, and at this point, just before the subsequent expiration, we disconnected the patient from the ventilator, increasing the expiratory driving pressure. And from this increase in expiratory driving pressure, we were expecting to have an increase in flow, which was the case. And if we compare this flow volume loop to the volume pressure curve obtained during a slow inflation of the respiratory system, the pressure here is a quasi-static elastic pressure. We had from the PEEP of 5 a continuous increase in volume with a continuous increase in pressure, suggesting that in these patients the airways were open and were communicating to the atmosphere. But in some patients, the pattern was different. Here you have the baseline expiration flow volume loop at PEEP of 5, and at this point we disconnected again the patient from PEEP 5, so we had the same expiratory driving pressure that resulted in no change in expiratory flow. And if we compare this flow volume loop with this patient to the volume pressure curve of this patient, you see that from 5 centimeters of water of PEEP up to almost 18 centimeters of water, there was no change in volume, and suddenly there was an increase in a volume with a subsequent increase in pressure, suggesting that in this patient, the airways were closed and not communicating with the atmosphere up to this critical opening value. It's important to have that in mind to make the distinction between airway closure and lung recruitment. So to conclude, we have limitations with the method we have been using in passively mechanically ventilated patients. It requires a full relaxation to have precise measurement. You explore the total respiratory system. You don't partition the lung and the chest wall. And you have a global approach. You have not a regional lung approach. But it's easy to observe. It's easy to perform at the bedside. And from this measurement, you get a better understanding of the lung pathophysiology and also a better way to set the ventilator. Thank you so much for your attention. I'm ready to take your question.